Welcome to Tokyo Institute of Technology. We are one of the national supercomputing centers in Japan. Currently, we have the second fastest supercomputer in Japan. We're currently ranked 22nd in the world. We have been as high as fourth back in 2010 when we had the first introduction of our Tsubame 2 machine onto the list. Of course, the machine will age, and not just as a resource center, as a research center in supercomputing. We have a number of groups, including mine, tens of people that are working with both our industrial partners and also research labs, such as those in DOE, like Livermore, Oak Ridge, so forth, in that we are striving to elevate our performance to the next generation. So we're planning for a Tsubame 3 update or renewal of a machine in 2016. And our Tsubame KFC machine, which you see here, is a prototype of the Tsubame 3. And one of the most important property is to basically work on power, because right now power is the limit on how much capacity we can afford in a system, especially in a university environment like ours. We cannot afford a 20 megawatt data center. In fact, the capacity we have on normal operation is about 1 megawatt, and then at maximum we can afford only 2 megawatts. So how do we, and university is not going to give us any more electricity. So how do we basically try to grow capacity, be at the top class, despite this shortcoming in our facilities? Well, so we really have to innovate in terms of our power performance, and KFC is an attempt to basically try to minimize energy, minimize the cooling power required, be able to do smart energy management, be able to govern and manage the machine, the job scheduling and so forth, in order to attain the maximum efficiency of the machine. And that we have been very successful in this endeavor, such that we were ranked number 1 on the Green 500 back in 2013, and also again in 2014. And on the top 500 list, that was announced just this morning. At least on that list, we're still the most power efficient machine in the world. Although the Green 500, the list may differ a little bit. The technology we use here is to use immersive cooling in a partnership with Green Revolution Cooling, and as you can see, this guy floating he's floating in oil. He's not being fried, so you can tell that the oil temperature is not that high. So it's not high enough to fry this person. So it doesn't really become a fried duck by any means, but still it's warm. It's about 35 to 45 degrees Celsius temperature. So the server being immersed, the temperature is about of the liquid itself will stay in that range. Because the fluid, in this case oil, has so much capacity, thermal capacity, even with the immense heat that's exerted from the server itself, especially the chips, the temperature gradient remains fairly small. So, and also that allows the chips to remain very cool. So the chips, like the GPUs, we have a comparative GPU. Each of these nodes have 4 GPUs, so it's a very dense architecture. And each of the GPUs in comparative air cooling configuration, we have a comparative node. The T case of such a node will rise to something like 80 degrees Celsius. Whereas being immersed, the temperature remains at 45 degrees Celsius, even at full load. So this allows the temperature to remain low, even with high load. This allows for the chips to operate at nominal temperature, and also be able to, for example, do clock or voltage boost when required to even have higher performance, but also keep the components temperature low, will allow to have a much longer life expectancy. That is, it will keep the temperature operating at a really nominal environment under some sealed, so there's no part of a component touching oxygen. So there was no corrosion going on. There are no moving parts, so we didn't get any vibration. Now, we don't know if Tsubame 3 will actually use immersive cooling, but definitely it will be using hot water cooling. It will have other innovative features that will accommodate a lot of the cloud and big data features into the machine. Some of those features you may see in the cloud have never been incorporated into a supercomputer. You will see for the first time in Tsubame 3, such as judicious use of component container technology, various types of facilitation of massive use of machine learning algorithms that will facilitate in the machine, and so forth. So Tsubame 3 will again likely become a very innovative machine. It will have not only high performance, not only it will be very high efficient, but also it will cover even much broader range of applications than what you've seen with Tsubame 2. And I hope that will set much higher standard for the HPC community and its strive for convergence with big data and cloud infrastructures. So that's my spiel. Okay. Thanks. Any questions?
Yeah, one question.
Sure.
That you lower the temperature, has that influence on the speed?
Yeah, so by lowering the temperature, there are two effects. One effect is when you have lower temperature, the leakage current goes down by the nature of the semiconductors. So the static leakage goes down. Also, by lowering the temperature, you can clock boost to higher frequency, because typically these clock boosting frequency and actually voltage boosting, it's decided based on the limits of a T-case temperature. The opposite happens. It's actually thermal throttling is the complete opposite of this effect. When the chip temperature goes too high, it slows down in order to prevent the chip from being damaged. So by having extremely high thermal capacity in terms of liquid, using liquid cooling to cool the chips, be it immersive or direct contact, this allows you to attain much higher performance and, of course, much higher stability based on these two physical principles. So we can typically we expect Tsubame 3.3 to have, even if you discount the improvements in the silicon process technology, we expect combining the thermal effects, better energy control, and so forth. We have some preliminary results that we published in which we can attain up to almost factor of 2 better power energy efficiency as compared to Tsubame 2 by combinations of all these properties, the cooling and also smarter control of the machine. So factor of 2, you may argue factor of 2 may be small, but you can keep your machine to be half as large, or you can procure a machine that's twice as large, and I think that's a huge step forward.
How hard will it be to swap out a board?
Yes, that's a very good question, and that was one of the other experiment we did. So actually, we put a crane on top. This is contained in a container, like a container data center. So we put a crane on top, and we have a wiring, and we're scheme where we can just hook up the node and just lift it up using a crane. Now it takes about 30 seconds to a minute to drain the oil, but after that it becomes serviceable. So we actually did an exercise of replacing all the adding SSDs to all the nodes, because also judicious use of SSDs was part of the Tsubame 3 design. So we did this as a post-mortem addition to the already immersive nodes. So we did a model measurement and figured out what was the biggest overhead. It turns out the lifting of the nodes from the immersive condition, servicing and again immersing them and reattaching the cables. The servicing part, actually attaching the disk, took about 18 minutes, but lifting the nodes up and immersing only took about 3 to 4 minutes. So of course you have to take other measures, make sure you don't get oily floor. But overall, it was very successful in proving that immersive, people may be worried about serviceability of immersive technologies, but actually the service overhead is quite small. And moreover, you get much better reliability by these immersion, because you will get rid of more mechanical motion, like getting fans, and you even have no oxidization. So we believe that the total cost of servicing is overall on the winning side because of this. Yes. Okay. Thank you.